In this video, I'm going to explain something about the dot product in 2 and 3 dimensions, namely this fact from last time, that the dot product is equal to the product of the norms times the cosine of the angle between the two vectors. Okay, so here's the setup. So we've got two vectors in R3 or R2. That's 3 space and 2-dimensional space. So let's just work with 3 space. So then one of the vectors is just given by a triple of numbers, and similar is also given by a triple of numbers. And the definition of the dot product of these two vectors is you multiply the corresponding components together and add. So u1 times v1 plus u2 times v2 plus u3 times v3. So that's the definition of the dot product in R to the n for any n. And the theorem is that if theta is the angle between the two vectors, u and v, then the dot product equals the product of the norms times the cosine of the angle between. And the proof is to apply the law of cosines. So here I recall what the law of cosines says. It's a generalization of the Pythagorean theorem to the case when the triangle is not a right triangle, and it says that c squared is equal to a squared plus b squared, but then there's this extra term of subtracting off 2ab times the cosine of theta, where theta is the angle between a and b, opposite side of length c. It's 90 degrees. Cosine of theta is 0, and so this term disappears, and you get c squared equals a squared plus b squared, as in the Pythagorean theorem. Okay, so here let's apply the law of cosines to the triangle formed by the two vectors and the vector v minus u, which goes this way, minus v, which is the vector of the same length, but in the opposite direction. Would have been fine. Okay, so our c is equal to this vector, and the norm, or the length of that vector squared, is what c squared is. Then we've got c squared is the norm of u squared plus the norm of v squared, and then the 2ab term times the cosine theta is equal to this. And then now we work in coordinates, or in components. So vector v minus u is you subtract component, and those are the components of v minus u. So v1 minus u1, v2 minus u2, and so on. And then the norm is you take each component, square it, and add that. So the norm of u is the u squared, add it up, and similarly for the norm of v, that's here. Then it turns out, we can expand minus u1 squared, and that becomes v1 squared minus 2 v1 u1 plus u1 squared. Similarly, all of these two terms we can FOIL out and get these terms, and it turns out then that the terms that are squared cancel. So this v1 squared cancels with the on the other side of the equation, and similarly for the u1 squared here, u1 squared there, they cancel, and so forth. And so what we're left with is the negative 2 v1 u1, negative 2 v2 u2, negative 2 v3 u3, and on this side of the equation, the right hand side, what we're left with is negative 2 the norm of u times the norm of v times cosine theta. So we get this, the minus 2's or negative 2's cancel out, and here we're left with the dot product. The dot product is commutative, so it's u dot v is u, and then that's on the right hand side is exactly what we are hoping to prove, that the dot product equals the product of the norms times the cosine of the angle between them. Okay, I want to do the following problem from Anton. It's on page 154, number 25, and it says a rectangular box has sides of length 10, 15, and 25 units. Find the angle between the diagonal, so here's this diagonal, and the side of length 25. Okay, and so the key is to use the dot product. That's involves the angle, and set up two vectors. The problem doesn't tell us what the vectors u and v are, so that's part of the challenge. So one vector is the vector that starts at the one corner of the box and ends at the other, so that's the diagonal of the box. I'm going to choose a coordinate system that has at the origin this corner of the box, and so then this vector u that's in green that corresponds to the diagonal of the box has components 25, 15, and 10, because it's going 25 in this direction, the x direction, if you will, 15 that way, and 10 that way. I could have chosen to set up the coordinate system in a different way. As long as I'm consistent, it's fine. Okay, so then let v be, well, I initially chose v to be the vector 25, 0, 0, so that's in red here, the vector in the direction along the edge of length 25. But to make the math a little bit easier, I chose or changed it to the unit vector in the same direction. It turns out either one of these two will give the same answer. The arithmetic or the numbers will be a little bit smaller here when I use the 1, 0, 0. Okay, so first let's compute the dot product, u dot v, of these two vectors. Since we're given their components, the dot product, we want to use the second formula here, and the dot product of u and v is 25 times 1 plus 15 times 0 plus 10 times 0, and that all adds up to 25. Next, let's use the other formula for the dot product, namely u dot v is also equal to the norm of u times the norm of v times the cosine of the angle between them. And that tells us that, well, first we have to compute the norm of u. Here's what u is. The norm is you take the square of each component, add that all up. So 25 squared, 15 squared, 10 squared, add that all up to 950, and then take the square root. Similarly for the norm of v, that's a little bit easier, and we just get 1. And so now plugging in to everything into this formula here, we know from earlier that u dot v is 25. Norm of u is square root of 950, norm of v is 1, and then we don't know, and we're trying to find cosine of theta. So we have this equation where the only variable now is cosine of theta, or theta, and then solving, we get that cosine of theta is this quantity here, and then using a calculator, we get that theta is 35.7 degrees, and that's the answer.